This is a look at the origins of the equations of motion. So let's look at a fairly typical general graph of velocity against time. Now we know that the gradient of a velocity time graph from our GCSE work is the acceleration. So we know that the acceleration is the gradient, and if we look at the gradient, we have final velocity minus initial velocity. That's the change in y. So we've got v minus u, and the time it took to make that change is t seconds. I just highlight those for you. So if we write that then, making v the subject, we'd have at equals v minus u. So then we would have v equals u plus at. And we'll call that equation 1. So there's our first equation of motion. The second equation that we can come up with, and what we're aiming for here really, is a set of equations which contain different sets of variables so that whatever variables we are given, we are able to work out the missing one. So here's one equation with v, u, a and t in it, but we don't have an equation yet that has the displacement, s, in it. Now we know that the displacement, distance travelled in GCSE terms, but the displacement is the area under the graph. So this area here is the displacement, and we can work that out in one of two ways. We could say it's the area of this triangle plus the area of this rectangle, or we could say it is the area of this trapezium, and that's what I'm going to do. So we say the displacement is the area under the graph, which is the area of the trapezium, which is half the sum of the parallel sides. That's those two sides, half the sum of those. So that's u plus v over 2 times the perpendicular distance between them, which is t. So now we have our second equation of motion. S equals u plus v over 2 times t. Now what we want to do is to substitute using an expression for t from this equation into this one so that we get rid of t in here. So then we'll have an equation in v, u, a and s. So that's what we're going to do next. So if we then substitute from equation 2 into equation 1 for t. So if we take equation 2, which is s equals u plus v over 2 times t, and we make t the subject, well, we'd have 2s, if we multiply up by the 2, over u plus v would be t. If we then put that into v equals u plus a times 2s over u plus v. Let's rearrange this slightly. Let's say we have v minus u equals a times 2s over u plus v. So then we have v minus u times u plus v equals 2as. If we square this out, we'll get v squared minus u squared, and then we'll have v times u minus v times u, so they'll cancel. So we'll have v squared minus u squared here is 2as. If we rewrite that then, we are there with our equation. We get v squared equals u squared plus 2as. And there's our third equation. Finally then, let's derive our fourth equation. So we had v equals u plus at, we had s equals u plus v over 2 times t, we called that 1, we called that 2, we had v squared equals u squared plus 2as, and we called that 3. Now, let's get an equation that has s, u, a, and t in it. So, no v. So, if we were to put this in here for v, in here for v, then we would have an equation which only has s, u, a, and t in it. So let's do that. So if we substitute from equation 2 into equation 1 for v, substitute from equation 1 into equation 2 for v, then you have s equals u plus at over 2 times t. So let's multiply this out. We've got 2u divided by 2 plus at. So we've got 2u over 2, which is u, plus a half at times t. So we have s equals ut. Let me start this again, I write it in red. We have s equals ut plus a half a t squared. And there we have our fourth equation. So we have 4 equations of motion: v, u, a, and t, s, u, v, and t, v, u, a, and s, s, u, a, and t. So we have combinations of variables in our equations which allow us to work out the missing one. Sometimes we'll use them in succession, and sometimes we can get our answer from just one equation. And with the equations of motion questions, there's often more than one way of going about it. So I said at the start that these equations only apply if the acceleration is constant. So let me take this away for now, and let's look at a non-linear graph. Now, you can see in this graph that if I was to say, well, the equation of motion v equals u plus at, well, does v equal u plus at? It does, but because this isn't constant, we can't work this out. We would have to say that we had an infinite number of tangents to this curve for us to work out the acceleration at each point. And that's not a workable proposition for us. If we were to say, well, we said before that S was u plus v over 2 times t. Well, it isn't, is it? Because S is this area, and that isn't u plus v over 2 times t. So hopefully you can see that the equations of motion actually do not apply if the velocity time graph is anything other than a straight line. It doesn't have to be proportional through the origin. It does have to be linear though. So that is an important point to remember. If you have a changing velocity, a changing acceleration, like for example in a roller coaster, the acceleration changes with your roller coaster cart as it goes around the track. As it goes down a slope, even on the track, the acceleration is changing. The slope is changing, the air resistance is changing, the acceleration is changing. You can't use the equations of motion there. You can work out an average acceleration or an average velocity or something like that, but you can't work out the actual velocity, the actual acceleration, because it's changing. So you need to have another way, and typically the other way is likely to be an energy consideration. So bear that in mind. Do not use the equations of motion if you don't have the constant acceleration condition satisfied. So our summary then, these are our equations. I recommend that you learn these. It may well be that you have them on the data sheet, the equation sheet that you're given, but having these in your head allows you more quickly to solve the problem. So I thoroughly recommend you learn all your equations. Use your equation sheet to check if you're not sure under pressure, but learn them.